So this is question 10 from paper 1 of the SQA Curriculum for Excellence Higher Specimen paper. We're asked to find the rate of change of this function at a particular value of x. Rate of change means differentiating. So we've to find f dashed of x. This is going to involve the chain rule. This is 4 times something cubed. Let's look at examples of some functions and their derivatives. What we get after we differentiate. Let's look at x cubed. You differentiate, you get 3x squared. The chain rule involves cubing something slightly more complicated than x. The same rule applies, but there's an adjustment. You have to multiply by whatever was in there differentiated. So for instance, if it was 2x minus 1, we would go 3 lots of 2x minus 1 squared, but then we would have to multiply by 2 because that's what we get when we differentiate 2x minus 1. If we, for instance, had x squared cubed, we would have 3 lots of that squared times whatever you get when you differentiate that x squared, which would be 2x. This is quite an interesting one because we can simplify this into 3 lots of x squared times x squared is x to the 4th. And 3 2s are 6, x to the 4th times x is x to the 5th. And of course this is x to the 6, x squared times x squared times x squared. And when we differentiate x to the 6 we get 6x to the 5. It's a nice little demonstration that the chain rule makes sense. So the rule is, if we have something cubed and we want to differentiate it, we'll get 3 times that something squared times whatever we get when we differentiate the thing that's pretending to be an x normally, like there. So that's the method. So we have to look at this function f of x that we've got, which is 4 times sine x cubed. Now the 4 doesn't matter, it just sits there and everything's multiplied by 4. So it's basically differentiating sine x cubed is the difficulty. So the result will be 4 times 3 times that squared times whatever we get when we differentiate that sine x. And that's a cos x. So there's our answer. It's 12 lots of sine x squared times cos x. And that's what we've to work out the value of when x is 5 pi upon 6. So it's 12 lots of sine 5 pi upon 6 squared times cos 5 pi upon 6. So there's another problem we have. Let's look at quadrants. 5 pi upon 6 is almost pi radians. It's pi upon 6 short of pi radians. So there's 5 pi upon 6. Second quadrant angle, and we're dealing with pi upon 6. So in the second quadrant, sine is positive. So this will be the same as sine pi upon 6 squared. Now pi upon 6 is 30 degrees. Value of that will come from an equilateral triangle, halved, of each of side 2. There's 2, 2, 2. There's your pi upon 6 up there, 30 degrees. And sine opposite over hypotenuse. Sine pi upon 6 is 1/2. So we said a second quadrant angle using pi upon 6 positive. So we've got a half squared times. And then cosine pi upon 6 adjacent over hypotenuse. Now Pythagoras in this, square root of 2 squared minus 1 squared, square root of 3 for this third side. Cosine of pi upon 6 adjacent over hypotenuse, root 3 upon 2. But it's not root 3 upon 2 because the cosine in the second quadrant will be negative. So there's what we have. A half times a half is a quarter. A quarter of 12 is 3. So 3 times negative root 3 upon 2. So this equals 3 times root 3. 1 times 2, multiply the top two numbers, multiply the bottom two numbers, and the answer is negative. Positive times negative is negative. So the rate of change of this function when x is 5 pi upon 6 is negative 3 root 3 over 2.